Bonjour. Well, that's the way we say hello in France. Hello, children. How are you people doing? I'm Saurabh Kumar Dutt, and I'm here to teach you people a little bit of mathematics. And in this lecture, we will be looking up geometric progression and its applications. Here, we'll be looking up what is the basic characteristic of a geometric progression, how we can find out the nth term of a geometric progression, how to find out the sum of a geometric progression when we have two different values of the common ratio. Then we'll also be looking up whether we can find out the sum of infinite terms of a geometric progression, and if so, what will be the formula. After this, we'll be looking up a sum which has come in boards and a special sum which will give you a very good analytical view of geometric progressions. I will also be providing you people with a second explanation which will ensure that everything is very well understood and there is no lapse whatsoever where you haven't been able to understand anything. So children, be here with me till the end of this lecture so that all of this be very well understood and assimilated. And all of this will be given to you as first we'll be starting off with a journey to this lovely place. Then I'll tell you about the traditions, the jokes, then the things that we can learn from this place, and also we will be looking up an awesome dish when after a lot of studies you'll be hungry. So I'll be serving you people that sweet delicacy so that you are really entertained. So children, let's quickly start off this lecture by first telling you about what this scintillating place is. This is Côte d'Azur, Mediterranean coastline, France. This is known as the French Riviera, where you will get to see celebrities, world's richest people throng and make a beeline. This is the place which is said to be having people to spend yearly $5 billion in the different places that are here, which are really worth seeing. Here you'll be surrounded by red mountains, the sandy beaches, and vibrant marketplaces which exhibit sophistication and fashion. I'm sure you will really like to this place, and you will find this to be very fine a place because this has 300 days of the sun and there is very little rainfall, as well as the weather all the year through is really awesome. You will get to see the color of the sea and the color of the sky to be one and the same blue shade. So I'm sure you will go there and enjoy yourselves with all of this. But do remember to tell all the people of France that you get to see bonjour. In this note, children, I'll be starting off this lecture by again saying bonjour, but at this time to geometry progressions, where first now I'll be discussing certain concepts, and after that then I'll be delving into sums so that you have a very good idea about this topic. Now children, to tell you people a few things about the concepts in geometry progressions, do remember that if say we talk about a geometric progression, do we say something like AR square, AR cube, and so on, right? So I'm sure you're getting to see that there is something which is missing. Yeah, Mary, can you tell me? Yeah, there is a comma which is missing, right? And is there something else that you can say? A plus sign. Very correct. So here children, if we talk about one of the things that is missing here, that is probably a comma that you can write between all of these terms, and when you do so, then this will be known as a progression, right? And if in place of writing a comma, let's say you want to write a plus sign, then this will no more be known as a progression, but now then it will be known as a series, right? So do remember this, that when you have the terms of any type of progression, right? It can be an arithmetic progression, it can be a geometric progression, it can be a harmonic progression. Between the terms, if you have a comma, then you say that that is a progression. However, between the terms, if there is a plus sign which is written, then that means that it is a series, right? Now we have this geometric progression, say, and now the special characteristic of all of these terms, as probably you can see from this, is there is a number r which has been multiplied to the term ahead, right, so that you can get to the next term, right? That means the first term has been multiplied with r to get to the second term, the second term has been multiplied with r to get to the third term, and so on. Moreover, this is said something like this: you have r, which is known as the common ratio, is given by the ratio of the second term to the first term, which is further equal to the ratio of the third term to the second term. That means if you find out the ratio of any two consecutive terms such that the term which comes later is in the numerator, then you will get the common ratio. And for the whole of the series, you will find that this will come out to be the same. Now, one special thing that I told you people, that if you talk about this r, this is actually the common ratio, right? So you require to remember this. Now, after this, if you talk about this a is what? A is the first term, as you studied in arithmetic progression also, right? So now children, as we know the special characteristic of an, or rather a geometric progression, that is the ratio of the consecutive terms such that the later term is in the numerator, always comes out to be a constant, which is the common ratio. Now we'll be interested in finding out the nth term. So if, say, you want to find out the nth term of a geometric progression, that is given by Tn is equal to a r raised to the power n minus 1. Now here children, as you know that a is the first term and r is the common ratio, n is the number of terms. So if you require the 10th term, then this will become a r raised to the power 10 minus 1, that is a r raised to the power 9. Now children, after you know this, now next I'll tell you people about how to find out the sum of n terms of a geometric progression. So let's say you have a geometric progression and you want to find out the sum of n terms. So as you normally do, say, you'll write the sum of n terms to be, say, some s, and in the suffix you will write n. Now this is given to be a times of r raised to the power n, from which 1 is subtracted, and in the denominator we have r minus 1. And here children, do remember that if you talk about the modulus of r, it is to be greater than 1. Now this implies that if you talk about the value of r, it should be a value which is to be more than 1 on the right hand side and should be less than minus 1 on the left hand side, right? Now when this value of r satisfies this condition, then this is the formula for finding out the sum of n terms. Now the other case is, if, say, you talk about the sum of n terms, then it is also written as a times of 1 minus r raised to the power n, which is divided by 1 minus r. This is when you talk about the modulus of r to be less than 1. So if you talk about the value of r, right, and then if you say that it is between minus 1 and 1, then you will say that this is going to be a formula to find out the sum of n terms. Now here, by the real line diagram, I'm going to show you which is the portion that you'll be talking about where this formula is going to be applicable. Now if you talk about this case here, let's say we have this which is a minus 1 and this point which is 1. So the ranges that we are talking about are actually these. That is, when we talk about the first case, it is going to be either on the right hand side of 1, right, or it is going to be on the left hand side of minus 1, right, something like this. So here children, this is how we are going to find out the value of the sum of n terms, and you will find that all of this, right, is found out by these two formulae, but there is a small fallacy which you can get to see, right? So if you talk about these portions, that is this portion and this portion, then this is the formula which is applicable. Now if you talk about this portion, right, in this portion the formula which is applicable is this one. That is, when the modulus of the common ratio is less than 1, then we apply the formula a times of 1 minus r raised to the power n divided by 1 minus r. Right? Do remember here that the modulus of the common ratio is to be less than 1. Now, when we talk about the modulus of the common ratio to be greater than 1, that is, if it is lesser than minus 1, or if it is greater than 1, then the formula applicable is this, that is a times of r raised to the power n minus 1 divided by r minus 1. Now, like I told you children, there is a small fallacy in what I told you. That means there is probably some error in what I told you. Were you able to assess it? Yes, Mary, can you tell me? Thinking. Good. Don't know. Well, I'll tell you. Probably you'll require a little more time and then you will easily be able to analyze it. If you talk about both of these formulae, I'm sure you're able to get to see here that if you'd multiply the numerator as well as the denominator by minus sign, then this will get converted to this formula. Let's see. If say now we talk about Sn to be equal to a times of r raised to the power n minus 1, which is divided by r minus 1. Now let's multiply the numerator by minus 1 and let's multiply the denominator also by minus 1. So as such it will lose its significance because both of these minus signs can be cancelled off. However, here we will get a times of 1 minus r raised to the power n, which is now going to be divided by 1 minus r when minus 1 gets multiplied to the terms of the numerator and also to the terms of the denominator. Right? Did you understand this? So this is the sum of n terms, and as you see that both of these are coming to be exactly the same. So it is just conventional that we remember that if suppose we talk about the common ratio to be one such that its modulus is greater than 1, then the formula applicable is the first one. And if the modulus of the common ratio is less than 1, right, then we talk about the formula applicable to be this, right? So these are the two cases where you can find out the sum of n terms. What if you want to find out the sum of infinite terms? Yes, Mary. Yeah, today you are in spotlight, so just give it a thought. What can you do? Okay, I'll give you some example. Now children, let us consider that we want to find out the sum of infinite terms of different geometric progressions. For that matter, let us first consider that you have a geometric progression which say is something like 1, and then you have the next one to be 10, you have the next term to be 100, you have the next term to be 1000, right, and you have the next term to be obviously 10,000. So as such you can see here that if you talk about the terms, then the first term is 1 and the common ratio is 10. As such, if you talk about the 100th term, then it'll be 10 raised to the power 99, right? This in itself is a very large number, and if you keep moving more distant from the first term, you will get larger and larger terms. As such, adding them all up and getting to a sum is something which is not possible, right? And as such, you will say that if you talk about the sum of infinite terms in such a sort of a progression, it is not possible. But if say we talk about another type of progression which say is something like this, that is, you have say 1 and then you have say 0.1 and then say you have 0.01 and then say you have 0.001 and further then you have 0.000 and 1, and all of that continues up to infinity. Then, like in the first case, if we want to find out the sum of n terms, it was something which is not possible. But if you talk about the second term, the second series, we get to see here that the terms are such that they are decreasing in value. So if you talk about the term which probably will be the 100th term, right, so it is going to be equal to 1 upon 10 raised to the power 99, right? So you see that it is something which is very small or infinitesimally small, something which is non-significant. As such, you can neglect it, right? So when you talk about a geometric progression such that the common ratio's modulus is less than 1, then we can find out the sum of the infinite terms, as the terms which come later will become non-significant or will hardly add up, right? Will hardly increase the sum of the addition of all the different terms, right? As such, here in this case, you can find out the sum of n terms. And what case is this? This is actually when you talk about the common ratio's modulus to be less than 1, right? So here, children, we have a formula that is pretty important, that is sum of infinite terms of a geometric progression when the common ratio is less than 1 is given by a upon 1 minus r, right? So this is an important formula for you people, so you should learn it. Now, children, all of this that I told you people, I'm quickly going to revise so that if there is any speck of doubt left, all of that gets perfectly clear, and then after that we will move on to sums. So these formulae I am putting up in rectangular boxes so that you can identify it in the text and learn it easily, right? So these are the different formulae that we have studied here. Although if you talk about both of these formulae, they can be said to be similar, as either one used won't give you a wrong answer. But you know the case. If you talk about the modulus of r to be greater than 1, then the first formula is to be used. And if the modulus of the common ratio is less than 1, then the second formula is to be used. And this is what teachers would like to see, that in whichever context you are using a formula, that is the one in which it is applicable. To get to certain answers is not exactly a matter. What is the matter is your concept should be perfect, right? And when your concept is crystal clear, to get to answers or to not to get to answers is something which can be a numerical fallacy, but at least it is not an error in the way you have your concepts, right? And that is something which is more important. Now, children, now that we have learned all of this, I'll like to quickly discuss this with you people so that if there is any doubt at any place, all of that gets cleared. So, children, the first thing that I told you people was that if, say, you have certain digits, alphabets, or anything which are arranged and there is a comma in between, then you say that that's a series. However, if there is a plus sign in between, then that will be said to be if you talk about a comma which is in between, then you say that that is a progression. And if there is a plus sign in between, then you say that that is a series, right? Now, children, if you talk about a basic characteristic of the terms which are in GP, that is, if you talk about the ratio of the consecutive terms such that the later term is in the numerator, then we have this ratio to be equal for any pair of consecutive terms, and that gives you the common ratio, right? And it is represented by small r. Now, if you want to find out the nth term, then that will be given by Tn, which is equal to a r raised to the power n minus 1. Right? Now, children, here further, if you want to find out the sum of n terms of a geometric progression, then there are two formulae here. First is when you talk about the common ratio to be greater than 1, that is when the value of r is either on the right hand side of 1 or it is on the left hand side of minus 1. Now, for that case, you will have a times of r raised to the power n minus 1 upon r minus 1, which will be the formula applicable to find out the sum of n terms. Now, if we talk about the sum of n terms, but the common ratio's modulus is less than 1, that means the value of r lies between minus 1 and 1, then the formula applicable will be a times of 1 minus r raised to the power n divided by 1 minus r, where both of these formulae are actually identical. Like I showed you, if you multiply the numerator and the denominator with minus 1, then multiplying it with the terms in the numerator and in the denominator, you will get it to be exactly the same as the second formula. As such, the first and the second formulae are identical, or in other words, you can say that they will give you identical results. But when what is to be applied, that is actually a concept, and that should also fall to be correct. So do remember, when the modulus of the common ratio is greater than 1, then the formula to be applied is this. And when the modulus of the common ratio is less than 1, then the formula applied is to be this. Okay, so here, children, next we discussed whether we can find out the sum of infinite terms of a geometric progression. Now, here we have a geometric progression such that the first term is 1 and the common ratio is 10. So 1, 10, 100, 1000, 10,000 and so on will be the different terms, right? So if we go to higher and higher terms, the value of the terms will become larger and larger and larger, and there is no extent to which you can keep increasing it, right? So as there is no limit to the value of each term, how can we find out the sum of all of these terms? As such, the sum of all of these terms will come to be something which is very close to infinity or probably infinity, right? And thus, as infinity is something which is not reachable, thus you won't be able to find this out. However, contrary to that, if say you have a geometric progression where the modulus of the common ratio is less than 1, then the terms will be like 1, 0.1, 0.01, 0.001 and so on. Now here you find that as you move towards the right hand side, that means as you move towards those terms which come later, you will find that those terms are becoming lesser and lesser and lesser, or in other words, their value is becoming insignificant. And thus, they will be adding up to the sum of all of these terms in an infinitesimally small way, and thus they can be neglected. And that is why the sum of infinite terms of a geometric progression when the common ratio's modulus is less than 1 can be found out. And in that case, we have the sum to be S infinity is equal to A upon 1 minus R. Right? So, Mary, is all of this clear? Yeah, do remember the modulus of R is less than 1 in this case. Okay? If it is greater than 1, then the sum cannot be found out, like I told you, because you can't get to how big a term can be, and every time every term is increasing the sum by a very big number. As such, the number will become so big that it will be something which is probably very close to infinity and you can't reach it, and that's why we will not be talking about the sum of those terms. So is everybody clear about all of these concepts? Okay, now children, one thing. Here we'll be discussing a sum and then there'll be a special sum, right? Now children, I want you people that you write all of these concepts once in your copies, learn it up, right? And after that, do write it once more without looking at what you did copy, right? With the help of this, then the assimilation of all that I've taught you people will be very nice and you'll be able to remember it for a long period of time.